So to start off, this structure is known as a sigma structure. Why would it be called a sigma structure? True. Let's go through and think about its reactivity. Okay, so there was a suggestion that the hydrogen was acidic, so that a base could come in and remove said electron. What would then happen to the electrons in that bond? Could go to the carbon. Okay, so we can draw that. That is generally not really where we would go with it, but that's okay. Negative charge. Where would we typically say it goes? It would go to the bond, resulting in the formation of a pi bond. Why would that be chemistry for this molecule? Why would it want that hydrogen to be removed? If we take a look at the product, that product is resonance stabilized. Lots and lots of resonance. Okay? It has so much resonance and is cyclic, in fact, that compound is known as benzene's technically true, that's not where I was going, aromatic. So what you talked about on Wednesday was going through and deciding, is it aromatic, anti-aromatic, or non-aromatic? The aromatic as a category is a huge category, and we can always kind of strive for that aromatic structure because it's super, super stable. Okay? And it is that stability that we can take advantage of, say, for a structure like this. If we ended up with that one in black, that hydrogen, even though it's bound to a carbon, is now very, very acidic, because if we remove that hydrogen, we can achieve aromaticity. Right? So it's looking at kind of that predictive ability of this. What is extra special about that structure? Okay, well, we called it a sigma structure. The reason it's a sigma structure is if we compare it to, say, our final product, the carbon where all the chemistry is happening has what bonds? Only sigma bonds. Okay? So we're referencing an aromatic ring that has a carbon that has only sigma characteristics. Okay? Officially, the carbocation down below only has sigma bonds too, but I don't think that one's as cool. So we'll just say sigma in quotes.
Well, doesn't that one have resonance? Then maybe the other carbon.
Fair enough. Actually, good point. Yeah. There's resonance there, which then means it no longer has full-on sigma, because the resonance would actually remove that sigma characteristic, and it would have some pi characteristics. Okay. So yeah, that's our sigma structure, and that's kind of our expected chemistry and what we take advantage of. So when we look at aromaticity, usually where we come out with is first off applying what the definition is. Is it aromatic? Is it anti-aromatic? Is it non-aromatic? And then we look at the application thereof. So one application is this particular structure. The other application was talked about on the previous slide, looking at acidity. Okay? We could also look at basicity. Actually, this one's looking at basicity, the reactivity of that nitrogen. The nitrogen in the pyrrole is significantly less basic than in pyridine because those electrons are being used to create an aromatic ring. Kind of makes sense? So we have to now keep aromaticity as an aspect or a condition to consider within our charge rankings. This is really just resonance. Okay, so it still fits in that category as resonance in our list of charge, size, electronegativity, all that fun stuff. It still fits in resonance, but it's now kind of this extra special form of resonance that it usually gets called attention to, particularly on the ACI. So which of these structures is aromatic, or which of these structures is the weakest base, and the reasoning will be because it's aromatic. Okay? So remember that word or that interplay behind it. Where this really gets into is now looking at that structure being an important one, because that's all of our aromatic reactions, which I believe he showed. Did we get to that? So yeah, everything on that slide is now the rest of the semester. Okay, so spend a hot second, memorize that. Okay, so now I'm done. So, you have questions? Not quite that bad, but it's pretty close. Right? The rest of what we'll be doing is just looking at each of those pieces in parts and explaining what's happening, why those things are present, what helps facilitate them. But for the most part, you need to know the reagents, and that's that first kind of box. It's not boxed, but this section is pretty much all of the reagents that you need to know. Okay? Once you know the reagents, they put on an individual piece. You now have a new structure. The issue is that all of those are starting with a benzene ring. Okay? Does it have to be just benzene? Okay? No. If I put on, say, a nitro group, I still have a benzene ring. That benzene ring could still potentially react. Will it react the same? Okay? Will the nitro have an effect on the ring? Yes. What is that effect? Well, that now effect comes out into our secondary categories of activators and deactivators. So we're looking, once we've put a substitution on the ring, what does that substitution do? And so if we take a look at the upper right, it's now just saying, I have a substitution, some X on that ring. If that X fits the activator category, then I would expect substitutions to happen at the ortho-para positions. Okay? You talk about ortho and para? So you guys are good with ortho, para, meta? Okay. That's true if X is electron donating. Okay. Well, what is electron donating? We're comparing it back to benzene. What is X in benzene? What is the formula for benzene? Ah, okay, so let's fix that. There we go. I hear some people mumble it. Yes, the formula for benzene is C6H6. If I now compare, come on, pen, these two structures, it's not resonance. What am I comparing? What is atom? How is atom X different? What am I comparing it to? Hydrogen. So when we're looking at this activator aspect, what we're trying to say is electron donating. So that means atom X has to have more electrons than hydrogen. Well, how many electrons does hydrogen have? 1. Okay? Not hard to have more than 1 electron. Okay? So a lot of things will fit in that activating category. Okay? Are there some things that could have less electrons than hydrogen? That one sounds a bit weird. Well, how could you have less than 1 electron? Okay? You could have no electrons, but if you have no electrons, you're probably not an atom, right? So how do you have less electrons than nitrogen, or than hydrogen? Let's go back to that nitro example. If we drew out the Lewis structure for that nitro, right? What's special about that nitrogen? For those of you trying to figure it out, it's in the middle of that, right? The nitro I just drew in. That nitro is positive. By definition, what's the issue with the nitrogen? It, by definition, has less electrons than hydrogen. That's why it's positive. Hydrogen had 1, wasn't positive. To become positive, you have to have less electrons than hydrogen, by definition. So yes, I have an atom with nitrogen, which we would expect to have more electrons, but those electrons are so preoccupied in the rest of the structure that the atom connected to the ring has less electrons than hydrogen. Well, if that's the case, it's not an activator, it becomes a deactivator. And notice what changes about the characteristics. Instead of directing to the para and ortho positions, as the activator did, what does our deactivator do? it directs to the meta position. So it changes where the substitution is going to occur. So if I can just classify whatever that X is, I can then dictate where my substitutions are going to happen. Okay? Which is a super popular question for the ACS, because this can get at synthesis very quickly and efficiently without having to dig into a crap ton of reagents. It's now just sequencing what reagent do you put on when, or what functional group do you put on when, and do you understand where that functional group would direct. Kind of makes sense? Okay, at least superficially. We haven't talked about any problems yet, so I expect some kind of confusion. After that, we've got the Birch reduction, which we've kind of already talked about. We add a little bit more trickiness to it because this time we'll include substitutions again on it, right? Just like we did with the EAS. And then the last two become extra fun. We get the NAS mechanism, N for nucleophilic aromatic substitution, which sounds a bit odd because what's happening in the electrophilic aromatic substitution is that an electrophile is reacting with the ring. Well, what's a nucleophilic aromatic substitution going to be? A nucleophile reacting with the ring. Right? So both options are possible. Though note, we've got tons of EAS reagents. Right? Why might we have tons of EAS? It's an electrophile reacting with the ring. What is the ring acting as? A nucleophile. Would I expect an aromatic ring to act as a nucleophile or an electrophile? So number one, it shouldn't react, right? Because it's aromatic. Okay, that's the first issue. Out of the gate, can't use that answer now. The next issue is now you're making it react. What would I expect it to do? Act as a nucleophile or act as an electrophile? Why nucleophile?
Because it has a lot of pi bonds.
All the pi bonds. All of those pi bonds are a source of electrons. It makes kind of sense that if the aromatic ring is going to be forced to react, clearly it is, it will act as a nucleophile. That is why we have tons of EAS reagents. That is why the NAS is very odd, because what's happening in the NAS? We're making the aromatic ring, a source of electrons, act like an electrophile. That's very kind of counterintuitive. That doesn't make any sense. Okay? The only way we can do that is by having very careful choice of our structure. And notice what is happening in the NAS to our benzene ring. I'm not starting with a general benzene ring like I did with the EAS. What am I starting with in the NAS? Substituted. It's a substituted ring. What is it substituted with? A bromine. What can you tell me about bromine? It's a good leaving group because large and electronegative. It can withdraw electrons. If it starts to withdraw electrons, what happens to the ring? Becomes positive. Stops becoming a nucleophile. Interesting. By putting a bromine on there, the ring could start to act like an electrophile, which it would need to in an NAS. But it's not just the bromine that's on there. What else is there? A nitro, a withdrawing group. Okay. For the NAS reaction to work, we have to have a ring that is massively deactivated. We have to have substituents on it to pull all the electron density out of the ring. That's what allows the NAS reaction to work. Okay? That's why we're very limited on those controls. Okay? When we move to the next one, an elimination addition reaction, note, one big change is we're no longer using sodium hydroxide, we're using sodium amide. What is the difference between sodium amide and sodium hydroxide? Sodium amide is more nucleophilic because the electronegativity. Nitrogen is less electronegative than the oxygen. Okay? What else? Not only is it more nucleophilic, it is also more basic. Turns out that in the elimination addition reaction, that sodium amide is acting primarily as a base. which is all sorts of weird. Right? The biggest weirdness out of this is that we don't get just a clean substitution. We get two products. What the F? Okay. Not only do we get two products, they're at two different locations. That's a bit bizarre. Okay. And it is doing something insanely bizarre. It is doing what is known as the Benzene intermediate. Anything look interesting about that word, Benzene? You're like, nah, it just looks like every other word in this class. The ein, why would the ein look weird? What does ein typically mean? Comes before dry? Sorry. Ein, oh, comes before zwei, I guess. Ein is typically for triple bonds, but benz is usually for benzene rings. So somehow or another in the course of this reaction, I end up with a benzene ring that has a triple bond. Huh. That seems a bit odd. I agree. I don't know why both of those reactions didn't get someone's name stamped to them, because I think those are pretty cool reactions, probably deserving of someone's name. But neither here nor there. Right? So those are all of our reactions. You should be spending some time committing this to memory. Not a bad idea to just sit down, print this slide, and just start memorizing it. Right? So again, we'll go through the basics behind this. Ideally, I can pick up the pace a little bit, and we just kind of cut through. Be like, well, this is what happens here, this is what happens here, and we just move on. Okay? Because we really just want to get to the point where we can apply all this stuff. So, reactions of benzene. Electrophilic aromatic substitution. What does electrophilic mean to you? Electron loving. So I need a species that would be electron loving. What could I draw that would make you go, yep, that's electron loving? Positive charge. But I don't want just a floating positive charge. I want a symbol tied to that positive charge. What symbol should we tie to make sure we know, yep, that's an electrophile? What's that? Nothing? Because if I put sodium, would that be a good electrophile? No, it's a horrible electrophile. So I could put a carbon. That's possible. So that's saying my electrophiles can only be carbons. I can't say have like bromine electrophiles. Oh, yeah, I could do that. What's that? How about just an E? Yeah, I agree. Let's go with an E for electrophile. So let's pick an electrophile. Any electrophile, I don't care. Now what do we want to bring in? Well, the next part of the name is aromatic. What is our classic aromatic structure? We can draw a benzene ring. Substitution is what? Exchanging an atom for another one in a chemical reaction. I've got two reactants. Let's draw a product. I now want to do a substitution where I exchange one atom for another. Well, that E is probably going to be involved in this. Otherwise, why would I draw it, right? What do I want to exchange that E for in the benzene? Why hydrogen? Why is the hydrogen the easiest thing to take off? Yes, I love it. What's that? No, I don't quite accept small. It's not horrible. Where's the hydrogen found? The outside of the structure. That makes sense. It's probably the easiest thing to break off. What if it had been a carbon? How would I have broken a carbon off? What would I have to have done? I would have had to break 4 bonds, put the E in, remake all those bonds to get back to aromaticity. Possible, not very likely. Okay, so more than likely, by just processing through the words that we've been given, we are probably going to do something like this. where the other piece left over would then be H. Well, what charge would I expect that H to be? Y plus. Because substitution, we have to balance of charge through the course of the reaction. Right? The electrophile was positive. If it's going to somehow bond to the structure is going to have to provide those electrons. If the hydrogen came off as a negative, well then, where did the electrons come from to bond to the electrophile? Does that make sense? So we can use the English language to take advantage of predicting how these reactions can work. Okay, make sense? Okay, so we now have an idea. This is EAS. But of course the question then becomes, how? Curses. So, how? What's the most reactive thing on the left-hand side? Charge. What charge? Positive charge. What do we need to stabilize that positive charge? How about some where are their electrons? In the pi bonds. Why would we go to the pi bonds and not to the hydrogen first? Why are the pi bonds more reactive? Pi electrons, as opposed to what electrons for our hydrogen? Sigma electrons. It's the sigma bond versus the pi bond. The pi bond is most likely the highest energy. Let's start our reaction there. Right? What would the result then be? Well, we still have the aromatic ring. Hey, look at that. We got the E now attached to our structure. I didn't touch any of the other pi bonds, though. I'd have a positive charge located here. This structure look kind of familiar? Oh yeah, this looks kind of like the structure that we just talked about in the foreshadowing. Yeah. Neat. Okay. Am I allowed to form a positive charge structure? Saying no. Okay, but we formed positively charged structures before. Why would I be allowed to form a positively charged structure? Why would I need to look at resonance? Yes. The driving force. We're looking for a stability. We are destroying aromaticity. So if I looked at an energy diagram, reactant, holy crap, crapolas, intermediate, that reaction's not going to happen. Okay? Something needs to stabilize that intermediate to make sure I can clear that activation barrier. If I can show there's resonance, we probably drop down a little bit, which then means my barrier also drops down a little bit according to the Hammond postulate. Okay? So, we should go through and show that resonance. And our positive charge, because these are resonance, double-headed arrow. Is there more resonance? Yeah. So I can show more resonance. Okay. I'm now out of resonance structures. So I've shown that this secondary carbocation is resonance stabilized, has a pretty decent potential for forming. This is still a really bad structure, because it's no longer aromatic. Okay? So there's now a large driving force to say, fix this. How does it fix it? As a hint, there's two ways. I can either break the electrophile off, or I could break the hydrogen off. If I break the hydrogen off, I can go through to form my final product. If I break the electrophile off, I reverse the reaction. Okay? So the big thing that's going to drive this is the relative stability of our electrophile versus the acid. Acid, thankfully, is something that's relatively easy to pop off, so we could go through and do this as long as that electrophile I'm starting with is sufficiently active to overcome the loss of aromaticity. Why do I no longer have aromaticity in my intermediates? I added what kind of bond? I added a sigma bond. That sigma bond is still there in each of those resonance structures. So I might call those sigma structures. Right? So everything we're doing in the EAS reaction is really just focusing on what the hell is E? Where did it come from? How do I get it? For some reason I'm trying to think Cotton Eye Joe. Where did it come from? Where did it go? Right? The rest of it is the same. You're just going through the sigma structures every single time. Right? And you might ask, well, are those sigma structures particularly relevant? Well, if it's benzene that you're starting with, no. If I start with benzene, I really don't care about the sigma structures because they're going to be identical. If I'm starting with benzene, the only thing I care about is what is the electrophile. Right? Because I'm doing a substitution for hydrogen. Every single hydrogen on benzene is identical because it's benzene. Okay? So with benzene, I don't care about sigma structures. The instant I change it from benzene to a substituted benzene, instead of it being a hydrogen, I put on a chlorine, or I put on an oxygen, or I put on a nitrogen, or I put on a methyl, or I put on a P coat. Okay? P coat. P coat. I'll put on something there. That's now going to change every other hydrogen. Those hydrogens are now going to become different, which means the sigma structures are going to have to be used to evaluate which hydrogen is the more reactive one. And the hydrogen that's going to be the more reactive is the one that generates the most stable sigma structures. If the sigma structures are bad, that hydrogen doesn't react. Kind of make sense? Okay, let's take a look at some electrophiles. Let's look at it pretty. Ta-da, pretty. So, we lose aromaticity in the course of that, so we want electrophiles that are stupidly positive. Okay, so if we take a look at those electrophiles, which of those is the most electrophilic? What's that? Nitrogen. Why? Nitrogen is positive charge. I agree. That nitrogen is very likely to be the most active electrophile here because of that positive charge. Okay? So she took the easy one. The rest of you are now screwed because you've got to figure out the other two. Left or right? Which one's more positive? Worst case, you guess and you're wrong, but we still talk through it. Okay, right. Why is the right one more electrophilic? Well, because it's right. Turns out that's actually correct. Why is the right one correct? Why is it the second most electrophilic?
Its resonance makes the carbon.
We have the pi bond there, which does resonance, making that carbon formally positive. We don't have a resonance structure for the other, for the bromine on the left, which means the acyl chloride, or the acid derivative, would be the stronger electrophile between it and bromine. Cool. Would all of these be expected to react with benzene? Well, the nitro probably, because it's the most electrophilic. It's probably going to react with benzene really, really quickly. Okay. The other two, being less positive, are going to become less likely to react. Well, I want them to react. How could I make them react? How can I make them react?
depending on the right structure, we could add an acid.
I can go through and add an acid, right? If I add an acid to that hydrogen, that oxygen becomes positive, it's going to want to move electrons away. That's going to make the carbon more electrophilic. That is possible. But then we've also added acid to the system, which could mess with our products. Because remember, we produce acid in the process of this. Okay? So I like that idea. We have to add something that helps polarize that structure. How does that even work?
Who is it?
It's literally not on the hook and it's ringing. Like, what do? Hang up? Hello? Let's try that again.
Unplug the whole phone.
It's the next move. I'll just call on the next line. Okay. So I need to add something that makes that carbon more positive, or for that matter, makes this bromine more positive. And now it's just... What could I possibly do? And now security's going to come yelling. Well, what do I want this bromine to do? I want it to take those electrons, right? Well, for it to take them, it might be helpful if it had something to, like, give them to, right? What would a characteristic be of that something? It should be somewhat electrophilic, but not able to make a strong bond. Okay? Well, if it was a nonmetal, that becomes problematic because that makes a strong bond. So let's try a metal. Let's try something like iron. And if we then go through and put bromines on either end of that, what happens? Well, that bromine can now polarize by sharing its electrons with that iron, causing the other bromine to become positively charged. I'm now adding a catalyst, okay? Which is exactly what Sam was suggesting by adding acid to the first one. We said the acid addition could be a bit problematic. Okay? What kind of catalyst am I adding here? What did that species act as? Be an electrophile if we were making an actual bond between metal or nonmetal and nonmetal. So I don't accept an electrophile. It is accepting electrons, but calling it an electrophile is a little bit weird. What kind of things accept electrons? Acids. Is that an acid? It's a Lewis acid. I'm adding a Lewis acid as my catalyst. Okay? That will help polarize those structures, making them more active and more likely to react. Same thing can happen out the other end. Yes, I could go through and try and add acid, and yes, that'll probably work, but I could also go through and add something like aluminum trichloride, which is also a Lewis acid. The electrons polarize, making that carbon extra electrophilic. Right? So in almost all of the electrophile formation reactions, we're adding some kind of secondary reagent, a catalyst, to force the reaction to occur. And that can be as simple as a Bronsted-Lowry acid, okay? But in a lot of cases it comes in as a Lewis acid catalyst. Okay? Which, this is going to be irritating, I apologize, sort of. So let's start with our list. Aluminum tribromide, Lewis acid. Aluminum chloride, Lewis acid. H2SO4, Bronsted-Lowry acid. H2SO4, Bronsted-Lowry acid. Aluminum chloride, Lewis acid. Aluminum chloride, Lewis acid. We're adding some kind of acid to help polarize our electrophilic species to get it to be active enough to react with our benzene structure. Because the benzene does not want to lose aromaticity, we need a catalyst. Okay? And that catalyst can be a strong acid, Bronsted-Lowry type. It is very typically some form of Lewis acid. Okay? So, there's our Lewis acid. What's happening is that iron being positive helps to polarize the structure. We can get a donation of electrons. They can shuttle the electrons to our positive chlorine, and we end up with a formal positively charged chlorine at the end. There's our electrophilic chlorine. Okay? We can do this to make carbons electrophilic. Okay? And notice again the highlighting of our colors. We're looking at positive carbons in both those structures. How could I possibly get R positive? What could I possibly do? What could it be connected to that would draw electron density away? A halogen, say like chlorine. What could my catalyst be to help polarize and cause that chlorine to come off? How about some kind of Lewis acid? Okay. Doing the exact same thing. Okay. How do I get the last one? Dang it. We draw that out. What we're saying is we have this structure. Does oxygen want to be positive? Okay. So what would a good resonance structure be for this to make sure that oxygen looked less positive? So while this may be a bad Lewis structure, does this give us an idea on where that functional group came from? Yeah, more than likely that came from an acid derivative that reacted with a Lewis acid catalyst. Okay, and sure enough, that is what happened. Okay, I personally like that last one the most because a couple things. Number one, that structure, while being our active electrophile, is not a good Lewis structure. Why is it not a good Lewis structure? Carbon doesn't have its octet. That's a bad Lewis structure because of octets. How would I make that carbon have its octet? Have the oxygen share electrons down, making structure of structures that weird triple bond looking thing. Okay? Which may look weird to us, and that's cool, that's fine. That is the better Lewis structure because all atoms have their octets. That does not make the oxygen the electrophile. Right? So again, use the charge to zero in on where the chemistry is going to happen, but that charge is not the end of your chemistry. Right? That oxygen still has a pair of electrons. It cannot act as an electrophile because nothing can come in and share electrons with it. It would exceed the octet. Breaking the electrons the other directions means carbon's taking electrons from oxygen, and that does not make physical sense. Okay? So we can look at that, get an idea that the chemistry is going to be happening near the oxygen. Pi bond breaks, the carbon's the electrophile. Make sense? Okay. Those two electrophiles are Friedel-Crafts, or named after two guys, Friedel and Crafts, who were the first ones to discover this sequence of reagents, making those carbons electrophiles in this fashion and reacting with aromatic rings. Okay? So the reactions get known as Friedel-Crafts alkylation and Friedel-Crafts acylation. Alkylation, because what are you doing? The root. Alkyl, you're just adding carbons. So an R group is just carbons. The other one is an acylation. Why? What's the root? That group is an acyl. Okay? So you may see those terms pop up. They're just in reference to that active electrophile. Okay? So Friedel-Crafts acylation and Friedel-Crafts alkylation. Those two reagents are very particular, and we would use them in different situations depending on what we're trying to synthesize. Fortunately, at this stage, we don't have the context to fully address that, so it will come back in a little bit once we start actually dealing with substituted structures. Okay. That said, I think the next slide talks about it a little bit. Oh, I'll actually tell you some answers here. The alkylation requires an active nucleophile. What did we say was an active nucleophile? Oh, we don't remember yet. That's cool, because we barely talked about it and we haven't looked at any structures, so don't stress. But remember that our alkylation requires active. Alkylation, active. The acylation does it whenever the heck it wants, okay, with all rings. There's some pseudo exceptions, but for the most part, those two statements are true. Okay? So the limitations of Friedel-Crafts alkylations. So let's take a look at what could potentially happen here. So ideally, what were we targeting? So the chloride shares with the aluminum. We would end up with our carbocation. The ring goes through, does its fun mechanistic steps, and we would end up with 3 carbons, right? Yeah, 1, 2, 3. Double bonds. Yeah? Okay. Anybody notice some issues to this mechanism that you're like, but Mike, I don't know about that.
Primary carbocation.
We have a primary carbocation. Our primary carbocation is stable. No. Turns out aluminum chloride is a strong enough Lewis acid that we can start to form small amounts of the primary carbocation. But primary carbocations aren't stable, so what are they going to do? They're going to rearrange. The product that we more than likely end up with is not that structure, but instead that one, because we end up doing a carbocation rearrangement to put the carbocation at the secondary position. Now we get the reaction to occur. Okay? That's a bit of a problem. Okay? So if we don't want a rearrangement to occur, that's where we can use the acylation, because the acylation isn't going to rearrange. The carbocation is formed and stabilized through that oxygen resonance. Okay? Kind of makes sense? But what if we go through all that, I still want just this for my answer. If I did the acylation, that eraser sucks. Let's switch to a different one. If I did the acylation and I made that an acyl group, and now when I go through and run this, yeah, I won't generate a rearrangement because I have a resonance stabilized carbocation right there. It's not going to rearrange, but the product I would end up with would be that. Is that the same as the red one? No, but I want the red one. So I've fixed the rearrangement issue, but now I don't get the right product. What can I do? I can do a reduction. What kind of reduction? Okay, I could do a Wolff-Kitchener, the N2H4KOH. Okay. What else could I do? Clemenson. Yeah, you guys had to come up with names, didn't you?
Mercury.
Okay, I'll accept that. I think that's the mercury and zinc and HCl. Okay. Sometimes you'll also see tin for this one. Pretty much you see acid and a metal do the reduction. Or the stupid dithiol one. with rainy nickel. That one gets a bit dicey because what does rainy nickel do? It will screw over your ring structure. So rainy nickel is probably a bad idea. Or just go easy, just add H2 and platinum. That'll do it too. That won't affect the ring. Why won't it affect the ring? Aromatic. Rainy nickel is just a nasty catalyst, and that's why it can mess with the ring. Okay. And it's usually with some harsher conditions. Okay, so there's lots of ways that you could go through and reduce away that carbonyl. So we could show that as a final product, and one of your answers will probably be the Friedel-Crafts alkylation. You go, oh, it's easy, one step. No, rearrangements, and you have to be concerned about that rearrangement popping up. Okay, kind of makes sense? Okay, so let me clear all that away. Let's just draw out that product, and we'll have a quick talk about activators. What did I say was a condition of my activator? Okay, electron donating. Okay, technically it is more electron donating. More electron donating than, and we're talking about atom X, the one immediately connected to the ring. That atom is carbon. Does that carbon have more electrons than hydrogen? Yes. Guess what the product is? Activated. By being activated, what does that mean about its reactivity? What's that? No, different term. Right idea. Maybe right idea.
Para or ortho?
If it's activated, it's more active than its starting material. So I do a Friedel-Crafts alkylation, I make a product that is more reactive than I started with. What happens? It continues to react. It'll continue to react at the para and ortho positions, as Elisa is referencing, and she knows para and ortho because she happened to memorize that activators direct the para and ortho conditions. And it does another substitution. Right? That other substitution would very likely go to the para position. Don't worry about knowing why yet. What can you now tell me about that atom? It's more electron donating than hydrogen, which means this structure is now even more activated, and it can potentially do another substitution. Your Friedel-Crafts alkylation reactions are susceptible to carbocation rearrangements, and they generate products that are more active than their starting materials. Okay? Which means they're very difficult to slow. Okay? So we have to be very careful using the Friedel-Crafts alkylation. It's in general just a bad reagent to use. Okay? So, carbocation rearrangements, we'll come back to that directing effect later, hopefully. Hybridization requirements. What would you expect in this Friedel-Crafts alkylation? What are we talking about trying to form? And these two structures would have to react to form. What can you tell me about that structure? That's a not stable electrophile. So is that likely to happen? Nope. If I can't form the electrophile, what happens? Nothing. There's no electrophile to react. Then the reaction doesn't continue through. Okay? So the Friedel-Crafts alkylation reaction doesn't occur unless you're looking at an sp3 hybridized carbon. Okay? So they have to be kind of alkane structures. If it's an alkane structure, you should be good to go. But the alkene and the alkyne, so vinylic or, I don't know what the other one is. We'll just call it vinylic for the moment. Okay. Don't react. So lots of issues with the Friedel-Crafts alkylation. This tends to be why you see the acylation a lot more frequently. After that, electrophiles with Bronsted-Lowry acids. Okay? I need to form this weird-looking nitro group with a positive charge on that nitrogen. Okay? Well, to do that, we need to start with nitric acid and sulfuric acid. That was our reagent sequence. This reaction I find super cool. Can anybody tell me why I find this reaction super cool? But those two charged atoms are positive and negative, so the overall is neutral. Maybe we can add some curved arrows in here. That might help. Make this a little more interesting. Whoops. Just ignore that. Everybody agree, right? What's happening? That first step? What kind of reaction is that first step? It's an acid-base step, right? We just transferred a hydrogen, right? What was the first one called? What was the name of that species? HNO3? Nitric acid, okay. And I react that with the next species, which was? Why are you laughing? What's so funny? I reacted two acids with each other in an acid-base reaction. Wait, I mixed an acid with an acid and somehow did an acid-base. Yeah. Yeah, I did. That's kind of neat. What happened? Nitric acid, it acted as a base. That's nitric acid. That's nitric base. Okay, that's kind of weird. What the heck? Why is nitric acid acting as a base?
It's a weak acid.
Nitric acid is, by definition, a strong acid. It just turns out it's not as strong as sulfuric acid. Sulfuric acid, being the stronger acid, will force nitric acid to act like a base. Okay? In so doing, we end up generating this structure, H2NO3, technically positive. Have you seen something of that form before? Yes, yes you have. H2O3, but not N because that's already there. If I did S, well, you might have seen that. That's kind of boring. C, H2CO3. What was that? That was carbonic acid. And what does carbonic acid do? It immediately decomposes into H2O and CO2. What did HNO3 decompose to? H2O and NO2. Okay? Everything fits the same patterns that have popped up again and again and again and again. Neat. I think that one's fun. Okay? If you guys were getting a test on this, that would be one of my test questions. But since you're not getting tested on it, oh well. Okay. The next one, this is fun. To generate the active electrophile, what did I do? I didn't do a very good job with the mechanism on this one. I kind of apologize. I did the same thing. It's an acid-base reaction to generate the active electrophile SO3H, okay, where one sulfate picked up a hydrogen from another one. So we're again doing an acid-base reaction that then decomposes and kicks out H2O. Okay. Is that a particularly easy reaction to run? What is sulfuric acid acting as a base. How do I get sulfuric acid to act as a base? We react it with a stronger acid. Well, sulfuric acid's kind of our cap. Right? So by just taking a solution of concentrated sulfuric acid and your compound, you can generate this electrophile. that electrophile can then react with the aromatic ring doing your substitution. The problem is you're now adding concentrated sulfuric acid to organic compounds. And what does concentrated sulfuric acid typically do? Kill things, okay, and destroy things. So it tends to be a very destructive reaction. That said, this reaction is highly reversible. Right? If I want to get this reaction to shuttle the other direction, I can just mix it with sulfuric acid and water. The water will act as a nucleophile, attack the sulfur, kick out carbon as a leaving group, right, which can then pull a hydrogen off of water, and we end up with, back to where we began, with a standard aromatic ring without the sulfate. Okay? So this reaction is the only one of these that is easily reversible. Okay? Typically, whenever we have reversible reactions, they get used because we can now do a protection of a position. Okay? So if you're doing a synthesis and you're like, but wait, these substitution patterns don't make sense, it might be because you're missing that you need to add a protecting group that was added and then removed in the course of the reaction, hiding that chemistry. Okay? Last one, how can I get positive carbon? Come on, you know an answer to this. Shower with compliments. Come on, give me something. Right, we could have done the aluminum chloride. Yeah, sure. But then that would have been on a different slide. Something else. Subtle hint up at the top. The title says electrophiles with Bronsted-Lowry acids. How could I make that structure by adding H+? So that means somewhere on here, well, all those carbons are the same, I have an H, which means what charge was that carbon to get this to react? It would have to have been negative. What was my starting material? What's that? You can start with an alkene, add a strong acid to it, add an acid that is non-nucleophilic. So for instance, if I did HBr, horrible choice, because what's going to happen? The bromide's going to attack because it's a better electrophile than the aromatic ring. Okay? So what acids could I add that are non-nucleophilic? Sulfuric acid, you mean like the ones at the top of the slide? Yeah. Yep. Sulfuric acid is a good choice. Okay. Again, we're probably leaning more towards concentrated sulfuric acid and not dilute, because if we diluted it, we're likely diluting it with water, and the problem with water, it's a nucleophile. So we'd want to, again, go with concentrated acid. Kind of makes sense? So that's how we can generate a bunch of different electrophiles. Okay. It's now just a question of putting those electrophiles in, attaching it on the structure, and being done with it. So memorize the electrophile, where it's coming, and then where it's coming from, the reagents, where it comes from, right? And that's pretty much just that first slide that just summarizes it and just lists it. Okay. Weird ones would be kind of the next sequence. Almost the next sequence. We could look at benzylic carbon reactivity. The benzylic position is extra special. Why is it extra special? If I say removed a hydrogen and made that a carbocation, is that a stable carbocation? Yes? Why? The resonance outward. The benzylic position is extra special as far as its chemistry because of that resonance stabilization. It is that resonance that drives a lot of chemistry with our aromatic structures. As we aren't looking so much now at the ring, we're looking at secondary effects on the periphery of the ring because of the ring resonance. Right? Which is where I made a massive typo on this, so we should just kind of like pretend that that didn't happen, and we should just erase that altogether. Okay? But since we can't do that, because of course I have to hit the next arrow and it pops back up. Okay. What is so horribly wrong with that first reaction? Oh God, it's really bad. Phew.
What would be a positive charge?
Yeah, that's sodium hydroxide, right? Hydroxide is negative. That negative comes in, takes the hydrogen, and puts the negative there, which would mean the product should be negative, not positive. So, good spot. Horrible, horrible job, Mike. Thank you for pointing out my failures, Jenna. Yeah, appreciated. So let's say we even fix that. Let's just make that negative. What else becomes problematic with it? I'm now removing that hydrogen from a carbon. Our carbon's particularly acidic. No, while this is more acidic due to that resonance, because that negative can potentially do resonance in, there's lots of electron density already in the ring. That's not very good resonance. Turns out that there's virtually no resonance stabilization of that. It is slightly more acidic than just an alkane, but not by much. Okay? Your pKa for that reaction is still in the 40s. Okay? So horribly, horribly, horribly bad reaction. When I was sending slides to Brian, I almost went back and deleted it, but I had already posted it for you guys, so I have to fix that some other time. So we can just kind of pretend that's not there until I have to advance the slide again, and then it shows up and we can relive my failures again. How about the next one? Would I expect that next reaction to work? What kind of reaction was it? Substitution. Under what mechanism? As a hint, there's only two answers. SN1, but maybe what you guys are being baited on is the why. Why is it SN1? Do I really need to remember all this? Yes, you need to remember all this. You're saying carbocation. I don't see a carbocation. Why are you saying there should be a carbocation?
If the bromine leaves, then there'll be a carbocation in the tertiary position.
So if the bromine leaves, do I form a stable carbocation? Yes. That's good reasoning for an SN1. Yeah, I like that. Okay, so good stable carbocation possible. Why would it be possible? Why is it stable? It's tertiary and benzylic. Tons of resonance there to help stabilize that positive charge. Yes, this would happen very, very fast under SN1 conditions. What's the other reason it's SN1? Steric hindrance is not particularly relevant per se. The steric hindrance is really going back to saying we form a stable carbocation. So it's not a steric hindrance argument.
It's not like a
There- There's no backside attack, which means we have a carbocation, which then means the nucleophile could attack from either the front or the back. We'd get an inversion in stereochemistry, true, all of that, but it's not a stereochemical product, so that doesn't help us. Tertiary still says stable carbocation. Sam, what's the last piece we should be looking at? Should be looking at the nucleophile. The nucleophile is weak. A weak nucleophile suggests SN1, not SN2. Okay, you could push that further and say that it's a polar protic solvent. Protic solvents favor SN1. All of those pieces you need to remember in stack. That goes all the way back to the first exam this semester and then all the way back to the exams from first semester. Okay, you have to go back and review those. You need that. Okay. Again, oh, there it shows up again. Look at that. How about that next one? Just in case anybody forgot. How about that last one? What happened there? Still substitution. Why are you now saying SN2 and not SN1?
Yeah, primary and strong.
Okay, I will accept the strong nucleophile as being a tip-off, but I will not accept the primary as being our tip-off. Why not?
Because SN2 doesn't create a carbocation.
true, but by saying SN2, he's saying the strong nucleophile comes in, does backside attack, kicks that out, there's no carbocation. So he's making the argument that there is no carbocation. I'm making the statement, I don't believe that,